Hello and welcome back everyone to another episode of the Reading Club, and we will continue covering the Presolve Reductions in mixed integer programming. That's again the paper by Gurobi developers about different types of Presolve reductions. So in the previous parts we covered I think most of the Presolve rules, and in today's part we will cover Presolve rules that are executed at the node level, right? So previously we consider all the Presolve rules that are used at the root node level, but now we will consider the Presolve reductions that are active during the tree search. Okay, so that's what we'll be looking at, and at the end we will also look at the overall summary of different Presolve rules. So let's get started. Okay, so the good news is that at the node level, there are no new Presolve rules, right? So whatever we have been using till now, we are going to still use some of those Presolve rules at the node level. So one of them is bound strengthening, right? So we have seen bound strengthening for one row at a time and multiple rows at a time as well. And this is bound strengthening that we'll be using at the node level as well, right? So the idea is that we will do, so when I say bound strengthening, it also means bound and coefficient strengthening, right? So typically we do not want to change the constraint metrics at the node Presolve levels, right? So when we are exploring the branch and bound trees, right? So the MIP that we solve at this node is very, very similar to the MIP that we solve at this node. And because of that, we can actually warm start it, right? So we can basically reuse the information from the basis of the LP solve of this node at this node. Okay, so that's the idea that we want to like, have the LP solves incremental. But if we change the constraint coefficients, right, then that's no longer the case. Then this is like significantly different. Otherwise, what's the difference between this? There's one or two bounds would have changed. Like, so main one branch would have say that xj is less than or equal to some particular value, let's say 5, right? And that would have caused some more propagations, right, because of this bound strengthening, and that's fine. But we do not want to change the constraints, right? So that's the main idea for behind any kind of pre-sort reductions that we'll see in the node level. And so bound strengthening, again, like we only change the bounds of the different variables, assuming that we have gone through multiple levels, right? So here we have taken multiple branchings, let's say, right? So after this, the problem at this over here is kind of quite restricted because it has gone through 3 branches. It is possible that there are more bound strengthening reductions are possible. So that's what this part captures it, right? So nothing very special. It's the same bound strengthening that we have seen before. But again, like this has to be fast as well, right? So this at the node level, we are going to enforce this Presolve rule at every node. So it has to be a lot faster than what we did at the root node, right? So at the root node, we can spend slightly more time, and in the bound strengthening over here, it's like, we have to be more restrictive and the bound strengthening. But nevertheless, it turns out that bound strengthening at the node level is far more effective than the bound strengthening at the root node level, because it's like bound strengthening is happening at multiple times, right? At every node it is happening, so that's why it is kind of a lot more effective. Right, so that's bound strengthening. The next that we are going to look at is called orbital fixing. Okay. So earlier we talked about symmetries in mixed integer programs, right? So this is still at play, and the only difference is that now in our branch and bound tree we have descended to some level, right? So we are, let's say, few levels down, and at this point of time, what symmetries we detected at the root node, right? Not all of them are valid, right? So there are fewer symmetries that are valid here, and that's what we want to find out. Like, so we in the Gurobi, they keep all the records of the symmetries that they have detected, right? So they store it as a permutation, like generators, right? What do they call it? Yeah, a set of generators, right? So this is basically a permutation of variables to variables, right? And using that, they basically encode one orbit or one symmetry kind of a thing. And not all of them are valid, but if some of them are valid after this level, then what they can do is that they basically say that they can do some tricks to update the bounds, right? So there is some variable xj, right? And it has some bound, let's say upper bound 5. Then there is some other variable, let's say xk, which is similar to xj. Then we can also set this upper bound to, from 7 to, we can set it to 5, right? So that's something that we can do. um, they say that you can doing the similar thing on the lower bound is kind of a bit tricky, but they haven't described it in detail, so I cannot really talk about it much. But that's kind of the idea, like what we have been doing at the root node. Again, like we are still doing it, but now we have slightly more information, right? So because we have branched and we have propagated a little bit more, we have more tighter bounds on a lot of variables, and because of that, the symmetric variables would basically receive tighter bounds as well, right? So that's orbital fixing. And the next part is very simple. It's called conflict propagation, right? So conflict propagation, right? So this is there are like a lot of papers as well. So some reading club episode, I will probably cover one of the paper about how to handle conflicts in MIPS, right? So and this is the idea. Okay, so we have our mixed integer programming branch and boundary, and let's say we are do solving LPs and everything, and let's say we reach at this node, and at this node we found this LP is either infeasible, or by either the LP is infeasible, or after doing some basic bound propagation we detected infeasibility, or somehow we detected infeasibility, or we find that we found some solution over here, right? Let's say the best solution, and the LP relaxation of this node's objective is let's say slightly higher. That means that nothing over in the below will ever give me a better solution than this solution. That means we can actually prune this node, right? So all of this are kind of cases of conflicts, and in those cases what we can do is we can try to learn from this conflict, right? So sometimes what happens is that a series of small explanations can help us reduce the size of the trees, right? So for example, let's say this branch we reached by, let's say x is greater or equal to 5, and let's say x is less than or equal to 3. Okay, not 3, let's say 7, right? Let's say this is x2, this is x1, right? So let's say because of this two decision, they are basically contradictory to each other. That's why we reach infeasibility. But it is possible that in other parts of the tree, right, we can still go that way, right? So here we can, at this part of the tree, we can still go x greater or equal to 5, and in other branch x2 less than or equal to 7, and that's kind of redundant, right? So because of this one and this branch we reach infeasibility, we should be able to figure it out that if we have taken this branch x greater or equal to 5 x1, then this branch will obviously give me an infeasible node, right? So this is the point of learning things from these conflicts. Okay, so how exactly do we do this? It's kind of using Farkas lemma, right? So we solve the linear program, right? And when we solve the linear program, we basically receive a dual ray because of this Farkas lemma. So it's basically like we have a lot of constraints, right? So there are a bunch of constraints, and for each of this constraint, let's say this is less than or equal to 3, this is greater or equal to 2, or something like that. And for all of them, we receive some multipliers, right? So this is y1, y2, y3, and so on. And it turns out that if we multiply this constraint by y1, this constraint by y2, and so on and so forth, we eventually end up getting a single constraint, like once we add them all up, right? And this is sufficient to explain the infeasibility over here, right? So this, along with the variable bounds, this is enough to explain the infeasibility, right? So this one constraint captures entire explanation of this infeasibility, and we can just either simply add it to the LP, but typically people don't add it to the LP. They just keep it in the bank, and of course there are limits on how many of this kind of constraints they can keep. And every time they branch and go for the bound propagation, right? So that's when they actually even propagate this special constraints as well, right? So this is a linear constraint, and otherwise there are also some conflict type of constraints which are kind of a lot more discrete, that if x1 is there are if x1 is greater or equal to 5, then x2 should not be less than or equal to 7, which is technically not linear if you have to encode that kind of relationship, but they can still be used for bound propagations, right? And preventing this extra subtree search. Okay, not that one, but just this one, right? So that's the idea behind conflict propagation, and people still do it, right? So that's another interesting thing. Gurobi says that they only keep at most 100 of these conflict constraints, and typically these conflict constraints are only like useful in the local context, right? So if we have found a conflict here, then this conflict constraint would be useful in like this area, but not most likely in this area, and they are kind of very, very dense, right? So we don't really want to uh, of course there are techniques to make it less dense, but that's a topic for another video completely, right? So we will see that in probably some other episode of Reading Club, where we discuss the conflicts in MIPS. Okay, so the last couple of things are related to probing. Okay, so we have seen probing before. It's basically like we take both the branches for a binary variable, one with a 0 branch and one with a 1 branch, and infer some information. Let's say if some variable has same bounds on both branches, then we can use those bounds. And in one case, if something is becoming infeasible, then we can know that this variable has to take this branch, and so on and so forth. Lot of things we have discussed in the probing part when we discussed it. But all of those things we can actually still reuse at the node level. Of course, at the node level, the probing has to be less. So we have to spend less effort on probing because we are doing probing at every node. And also, when we discussed probing at the first time, we also discussed a few things like lifting and all those things, which actually modify the constraint matrix. So at the node level, when we do probing, we don't do any of those things. Okay, so we only focus on tightening of bounds, and that's all. Right. So probing, again, like there are two types of probing, which is called global, which is kind of things that we do at the root node, and local. Right. So this is the kind of probing that we do, taking into account the local bounds at the node, at the current node, right? So let's say if we have this tree, right? So the bounds for the variable at this node might be significantly different than the bounds over here. And if we do any kind of probing using this bounds, then it is only valid in this subtree, right? It is not valid for the entire subproblem, entire MIP, right? So that's called local probing. And for the global probing, it's like we can still do probing at this node, but we do not look at this bound. Instead, we look at the bounds that are over here, right? So at the global bounds. So if we do it that way, then it's called global probing, right? So it's basically continuation of the root node probing that we stopped over here, and we are still continuing, but probably we'll have some more information as well. Okay, so that's global and local probing. Again, like all of those things are very, very useful, have a lot more impact than the probing that we did over here, because these probings, both global and local, they are applied at every node in the search tree, right? So that's pretty much all the node presolve rules that I wanted to discuss. That's just 5 of them that we just quickly discussed. And now let's take a look at the effects of individual presolves, right? So which presolves are actually a lot more, impactful than the other presolves. Okay, so this is an overall summary of all the presolve rules that are listed in that paper, right? So starting from model cleanup, single row reductions, single column reductions. They're all in families. And here I have listed down how many instances are affected by that particular Presolve rules, and what's the gain in time for the affected instances, right? So 1.11 means 11% gain in time. That's basically saying that if we turn it off, then it will take 11% more time to solve those instances. And this is the overall gain in time for all the instances, regardless of whether they are affected by it or not, the entire benchmark set. Okay, so this is like the times for instances that were taking at least 10 seconds to solve, the third row in that benchmarks. Okay, so overall, again, like the impact of Presolve rules is very high, right? So 99% of the instances are affected, and it gains about 900% improvement in time, right? So without the Presolve, it will take 9 times more time to solve those instances. Right, so that's why like the entire Presolve rules are far more important. If we go down to the individual Presolve rules, none of them are actually causing that much change, right? So the biggest gains I have highlighted, they are like more than 10% gains. I have highlighted them in green, right, over here. And if you look at the family levels, right, so single row Presolve reductions or single column Presolve reductions, none of them are actually even gaining 200%, right? So sorry, even 100% of the gain, right? So this is kind of an important thing to notice, that individual Presolve rules or even a single family of Presolve rules are not as effectful as the entire Presolve, all Presolve rules together, in the sense that it is far more important to have meaningful interactions between Presolve rules than an individual Presolve rule, right? So if it's kind of okay if we do not have few of these Presolve rules, but it is a lot more important that we have good interactions happening between these Presolve rules, right? So one Presolve rules might be doing some reductions, and that would trigger some other Presolve rules, and all of that is kind of a lot more important. Okay, so some of them can be safely removed, like, or if you are building a MIP solver from scratch, you might be able to skip some of them. For example, probing at a single row level, it is not really affecting a lot of instances. Only 22% instances are affected, and on the instances where it is affecting, it's only gaining like 1% in terms of time. So you can safely ignore implementing that one. But then if we skip implementing single ones like that, a lot of them are actually not really that impactful, then we will actually end up reducing this gain as well, right? So that's because like this Presolve rules might not be individually effectful that much, but in terms of overall Presolve reductions, if we eliminate a lot of these Presolve rules, then combined together they might cause bigger harm than individual ones. Okay, so now let's take a look at which Presolve rules were particularly more effective in this set of Presolve rules. I don't think they have listed down all the Presolve rules that they have in the Gurobi. They have listed the few of them which are actually important ones in the videos. I even filtered some of them which were not impactful. So not all, this is not in the complete set of Presolve rules, but it's rather at least the important Presolve rules they have discussed in the paper, right? So one of them is model cleanup. 10% improvements in terms of overall time affects 94% of instances. This one is the biggest, has the biggest impact, which is implied free variable, affects about 80% of instances, and on the affected instances, the gain is 54%, right? And overall, the gain is 42%. It's the single Presolve rule that has more impact than this entire family, right? So that has 26% improvement, whereas this one has this single Presolve rules has 42% improvement. The other impactful are click merging, must have Presolve rule, probing at the root node level. And it turns out that probing at root node level is more impactful than probing at the node level, including global and local probing. It's probably because the work limits over here are higher compared to the work limits at this level, right? So node Presolve level. So yeah, that's another interesting thing to notice. The bound strengthening at the node level is far more effectful than bound strengthening at the single row level or bound strengthening at multi-row level, right? So um, yeah, so these are the set of all interesting Presolve rules. Lot of Presolve rules are kind of they have overall lower impact, but that's because they affect very few percent of instances, right? So, for example, SOS reductions, they don't really that those Presolve reductions are not really impactful on huge families of instances, but when they are effectful, they it they bring huge gains, like 26% gain over here, and here that is semi-integer bound strengthening, semi-integer or semi-continuous variables bound strengthening. It's a 36% gain, although it only affects like 1% of the instances. Okay, so there are a lot of Presolve rules like that uh, which do not really affect a lot of instances, but affect have big gains. So, like for example, orbital fixing has like 77%, right? So this is symmetric variable. This has to do with symmetric variable and the things that we discussed in this video earlier, right? So that's I think all about the Presolve rules. I hope you liked it. So see you in the next episode. Bye.